2.8 billion miles from the Sun, a planet is doing something that should be impossible. Its clouds are vanishing. Its auroras glow in places they have no right to exist. Diamonds may be raining through its interior right now, and the storms that scientists expected to last forever keep disappearing. We are going to Neptune. We will watch its skies strip themselves bare, fall inside a world where it rains diamonds, and discover a moon that is slowly being pulled apart. If you enjoy the journey, subscribe and leave a like. It helps more than you know. Now brace yourself. We begin. Picture the farthest highway you have ever driven. Now multiply it by every road on Earth. You still would not be close to Neptune. This planet sits 2.8 billion miles from the Sunday 2.8 billion. To put that in your head, if you drove a car at highway speed without stopping, day and night, no brakes, no sleep, it would take you more than 5,000 years to get there. The Sun, which looks massive from our backyard, appears from Neptune as a tiny bright dot, barely brighter than a star. For most of history, scientists looked at Neptune and assumed the same thing: frozen, still, a dead ball of gas parked at the edge of our solar system, too far from the Sun to do anything interesting. It had been sitting out there for 4.5 billion years. What could possibly be happening? That assumption turned out to be one of the biggest mistakes in modern planetary science. Neptune is the 8th planet from the Sun and the last one on the official map of our solar system. It has a diameter of about 30,000 miles, which makes it roughly 4 times wider than Earth. If Earth were a golf ball, Neptune would be the size of a basketball. It is an ice giant, a category of planet that is completely different from the gas giants like Jupiter and Saturn, and completely different from rocky worlds like Earth and Mars. Ice giant sounds simple. It is far from it. The word ice here does not mean frozen water sitting on a surface. It means a thick, hot, pressurized soup of water, ammonia, and methane packed so tightly that it behaves like a fluid and a solid at the same time. The temperature at the cloud tops drops to around -360 degrees Fahrenheit. That is cold enough to freeze oxygen out of the air. Yet deep inside the planet, temperatures reach thousands of degrees, hotter than the surface of the Sunday. That gap, freezing cold at the top and blazing hot inside, creates chaos. Scientists spent decades building models of how Neptune works. They used what they knew about gas giants, about distance from the Sun, about how planets form and age. The models were clean, predictable, they made sense on paper. Then the telescopes got better, and Neptune stopped making sense. Bright white clouds that had been visible for years began vanishing. Storms the size of continents appeared and then disappeared within months. A spacecraft captured images of a magnetic field so twisted and off-center that engineers thought their instruments were broken. And just recently, the most powerful space telescope ever built turned toward this frozen, distant world and detected something glowing in places it should never glow. Every answer scientists thought they had about Neptune has been replaced by a bigger question. There are 14 confirmed moons orbiting this planet. One of them orbits backwards. One is slowly being torn apart. Another hid from scientists for decades, invisible inside old telescope images until someone looked a second time. This is where our journey starts. At the edge, in the cold, at a world that everyone ignored for too long. Because the planet that was supposed to be the most boring one in our solar system just turned out to be one of the strangest, and we have barely scratched the surface of what it is hiding. Neptune moves, just very, very slowly. It takes this planet 165 Earth years to complete a single trip around the Sunday. 1 year on Neptune lasts longer than any human has ever lived, longer than the United States has existed as a country, longer than the French Revolution, the Civil War, and both world wars combined. When astronomers first discovered Neptune in 1846, it was sitting in a specific position in its orbit. Scientists marked it, tracked it, watched it inch forward year by year through their telescopes, and in 2011, 165 years after that first sighting, Neptune finally returned to the exact same spot in space where humans first laid eyes on it. One lap, 165 years. That was the first time. Hold that thought, because it changes the way you have to think about everything scientists know about this planet. Every observation ever made of Neptune, every photograph, every measurement, every storm tracked and cloud mapped and moon catalogued covers less than one full Neptunian year. We have watched this planet for one lap around the Sunday, one season cycle, one complete rotation of whatever weather system drives its atmosphere. Imagine trying to understand Earth's climate by watching it for a single day. You would see weather, you would see clouds moving and temperatures shifting, but you would miss winter, you would miss summer, you would miss drought cycles and hurricane seasons, and everything that only shows up across longer stretches of time. That is exactly where Neptune science stands right now. Neptune's orbit is enormous. The path it traces around the Sun stretches across a distance so wide that if you laid the entire orbit flat and tried to drive across it, it would take tens of thousands of years at highway speed. The orbit itself is almost perfectly circular, which is unusual. Most planets travel in a slightly stretched ellipse, getting a little closer and a little farther from the Sun as they move. Neptune barely wobbles. This circular orbit means its distance from the Sun stays almost constant, which means the amount of sunlight hitting it changes very little over its long year. Scientists expected this to make Neptune one of the most stable and predictable planets in the solar system. Instead, they found storms appearing and disappearing within months, cloud systems forming and vanishing across just a few Earth years, temperature shifts across the planet that seem impossible given how little the sunlight changes. Something inside Neptune is driving this, something that does not depend on the Sun at all. In the 1980s, scientists pointed telescopes at Neptune and made careful maps of its cloud bands. In the 90s, they made more. The images looked similar across those decades. Bright white streaks, dark storm systems, a general stability that seemed to confirm the frozen, quiet model everyone had accepted. Then, within a few Earth years around 2023, those clouds nearly vanished. Gone. A planet that had looked the same for decades suddenly looked bare and dark. 165 years to orbit the Sun, and in less than a decade, the whole face of the planet changed. Whatever is happening inside Neptune moves on its own clock, a clock we are only just beginning to read. And the story of how we even found this planet in the first place is one of the most remarkable moments in the history of science. In the 1840s, two scientists in two different countries who had never met solved the same impossible problem at the same time without knowing the other existed. Their names were John Couch Adams and Urbain Le Verrier. One was British, one was French, and both of them were doing something that had never been done before. They were trying to find a planet they could not see. Here is the situation they were working with. Uranus had been discovered in 1781. Astronomers tracked its orbit carefully for decades, charting exactly where it should be at any given time based on the known laws of gravity. But Uranus kept drifting slightly off course, not by much, tiny fractions of a degree, but it was consistent. Uranus was being pulled somewhere it should not be going. The only explanation was gravity. Something massive was out there, beyond Uranus, yanking on it. Something nobody had discovered yet. Adams attacked the math first. He spent years calculating what size this mystery object had to be, and exactly where in the sky it had to sit to produce the wobble they were seeing in Uranus. He finished his calculations in 1845 and sent them to the Greenwich Observatory in England. They did not follow up immediately. The letter sat. Le Verrier reached the same answer independently in 1846. He sent his coordinates to an astronomer in Berlin named Johann Gottfried Galle. Galle pointed his telescope at the exact location Le Verrier specified. On his very first night of searching, September 23, 1846, he found Neptune, sitting within 1 degree of the predicted position. 1 degree. In a sky full of thousands of stars, two mathematicians calculated the location of a planet they had never seen, and they were almost exactly right. This moment matters more than just a history lesson. Before Neptune, every planet humans discovered was found by looking up and noticing something that moved against the stars. Someone saw it, then figured out what it was. Neptune reversed that process entirely. Scientists figured out what had to be there, calculated where it had to sit, and then looked. It was proof that math could see further than any telescope. Within 17 days of Neptune's formal discovery, an astronomer named William Lassell turned his telescope toward it and found its largest moon, Triton. Less than 3 weeks after the planet itself was confirmed, one of its moons was already logged. The solar system was giving up its secrets faster than anyone expected. But here is the detail that still bothers astronomers today. When researchers went back through old records, they found that Galileo Galilei had observed Neptune twice in 1612 and 1613. He drew it in his notebooks. He noticed it was close to another object in the sky. He even noted that it appeared to have shifted position between sessions. He did not follow up. He moved on. Neptune sat undiscovered for another 230 years because the most famous astronomer of his era glanced at it and looked away, which raises the question of what we might be looking at right now in our own observations and missing for the exact same reason. Galileo Galilei had one of the sharpest minds in the history of science. He built telescopes good enough to find moons orbiting Jupiter. He tracked the phases of Venus. He mapped the craters of our moon in detail that shocked the scientific world. And in 1612, while recording the positions of Jupiter and its moons, he pointed his telescope in the right direction and drew Neptune in his notebook. He called it a fixed star. To be fair, Neptune moves incredibly slowly across the sky. In a single night of observation, it barely shifts. From one session to the next, the change in its position is almost undetectable. Galileo had good enough instruments to see it, but his sessions were too short and too spread apart to catch the motion clearly. Still, his own notes tell a more unsettling story. On 2 separate nights during that observation period, Galileo actually noted that the star near Jupiter appeared to be in a slightly different position than before. He wrote about it. He acknowledged something was slightly off, and then he concluded it was probably due to an error in his previous measurement and moved on. The planet was right there. The evidence was in his own handwriting, and he explained it away. This is one of the most studied near misses in the history of science, and researchers find it fascinating for a specific reason. Galileo was not being sloppy. He was applying the best scientific thinking of his era, which assumed that stars are fixed and do not move. He had a framework. The new data did not fit the framework, so he blamed the data. This pattern, dismissing a strange result because it does not match expectations, has repeated itself throughout history, and it is showing up again with Neptune today. For decades, scientists built models of how ice giants behave. Neptune was supposed to be cold, still, and slow. When early observations hinted at unusual activity, researchers often concluded the instruments were at fault or the data was incomplete. It took years of repeated, consistent anomalies before the scientific community accepted that Neptune was genuinely behaving in ways the models could not explain. Galileo's miss has a second layer that makes it even more remarkable. After Galilei formally discovered Neptune in 1846, astronomers went back and searched historical records for earlier sightings. They found Galileo's notes. They calculated exactly where Neptune was on the nights he was observing. They confirmed that the object he drew and dismissed as a fixed star was, without any doubt, Neptune. Then they found something stranger. A French astronomer named Jérôme Lalande had also observed Neptune in 1795, more than 50 years before its official discovery, and had also dismissed the observation as an error. 2 of history's skilled astronomers had Neptune in their notebooks and let it go. The planet that has been full of surprises for modern scientists had already been hiding in plain sight, ignored twice. before anyone knew to look for it. And now that we know where to look, every new image from modern telescopes is uncovering things that make even the discovery story seem ordinary. The winds alone are enough to make your jaw drop. Imagine standing outside during a hurricane. The strongest hurricane ever recorded on Earth hit wind speeds of about 215 miles per hour. Trees snapping, buildings losing their roofs, cars flipping over. Now imagine winds moving at 1,200 miles per hour. That is Neptune. The fastest winds in our entire solar system are not on Jupiter, the biggest planet. They are on Neptune, the smallest of the 4 giant planets, sitting billions of miles from the Sun with almost no solar energy to fuel them. 1,200 miles per hour is roughly 1.5 times the speed of sound in Earth's atmosphere. A wind like that would not just knock you down. It would carry you across an entire continent in hours. These winds were measured by tracking cloud features across Neptune's atmosphere over time. Scientists watched bright streaks move from one side of the planet to the other and calculated how fast they had to be traveling. The numbers kept coming back the same. 1,200 miles per hour, sustained, consistent, planet-wide. The most baffling part is the energy source. On Earth, wind is powered by the sunday. Sunlight heats the surface unevenly. Hot air rises, cool air rushes in, and you get wind. The more solar energy hitting a planet, the more powerful its weather system can be. Jupiter and Saturn get more sunlight than Neptune, and they still produce slightly slower maximum wind speeds. Neptune receives roughly 900 times less sunlight than Earth. 900 times. At that distance, the sun provides almost no heat to drive weather. By every model scientists had built, Neptune should be the calmest of the 4 giants. The storms are driven by something else, something from inside the planet. Neptune radiates more heat outward than it receives from the sunday. Significantly more, the internal heat bleeding out from the planet's core creates temperature differences in the atmosphere, and those differences drive winds the way solar heating drives winds on Earth. The engine is buried deep inside the planet, invisible and still pumping out enough energy to spin storms at supersonic speeds. This internal heat source is one of the great mysteries of Neptune science. Scientists have a few ideas about where it comes from, and one of those ideas involves something that sounds pulled from a fantasy novel. But that comes later. There is another aspect of these winds that takes the strangeness even further. They blow in the opposite direction of the planet's own spin. On most planets, winds follow the rotation. Earth's major wind systems align with the direction the planet rotates. Jupiter's famous bands flow in alternating directions but are still organized around the spin axis. Neptune breaks this rule completely. The entire atmosphere, at certain latitudes, streams in the opposite direction of the rotation below it. Scientists call this retrograde wind flow, and they are still debating how a planet builds an atmosphere that fights against its own spin in such a systematic way. 1,200 miles per hour, no solar fuel, blowing backwards, and the color of those winds, the electric blue shimmering at the top of the atmosphere, has its own strange explanation. From space, Neptune looks like something out of a dream, a deep electric blue, richer and darker than Earth's oceans, more vivid than any natural color you would expect from a planet billions of miles away in the cold dark of the outer solar system. That color is not an accident, it is chemistry. Neptune's atmosphere is made mostly of hydrogen and helium, the same ingredients found in most giant planets. But mixed into that atmosphere is a small percentage of methane gas. And methane has a very specific relationship with light. When sunlight hits Neptune, it carries every color of the visible spectrum: red, orange, yellow, green, blue, all of it arriving together. As that light passes through the methane layer, the methane molecules absorb the red end of the spectrum. They pull the red out of the sunlight, the way a sponge pulls water off a table. The blue light passes through and bounces back out into space. That reflected blue is what reaches our telescopes. That is the color we see. The process is called selective absorption, and it works the same way a colored filter works in photography. The methane layer is essentially a filter that strips red from the sunlight and leaves only blue behind. Here is where it gets interesting. Uranus has almost exactly the same atmosphere, the same hydrogen, helium, and methane mix, the same basic chemistry. By this logic, Uranus should look exactly like Neptune. It does not. Uranus appears a much paler, almost washed-out blue-green. Scientists spent years debating why two planets with nearly identical atmospheres look so different. Recent research points to a layer of haze sitting above the methane layer on Uranus that reflects extra white light back out, diluting the vivid blue. Neptune's atmosphere appears to be clearer at the upper levels, allowing the deeper, richer blue to dominate. Even something as basic as color turns out to hide layers of complexity. The blue is also what made Neptune so difficult to observe before dedicated telescopes. From Earth, it appears as a tiny pale dot, easily mistaken for a distant dim star. The color that makes it so striking in close-up images actually works against it when viewed from far away. It blends into the background of space. Methane does more than just color the planet. It forms clouds. At high altitudes, where temperatures drop far below anything survivable, methane gas freezes into tiny ice crystals. Those ice crystals cluster together into bright white cloud bands that streak across Neptune's blue face. For decades, those clouds were a permanent feature of every Neptune image. They were the white lines you could count on seeing in any photograph. And then, within a span of years that shocked the scientific community, they almost completely disappeared. The clouds were there, then they were gone. And the reason they vanished connects Neptune to the Sun in a way nobody predicted, across a distance of nearly 3 billion miles. That connection is one of the most surprising discoveries in recent solar system science. Before the clouds started vanishing, there was already a behavior in Neptune's atmosphere that scientists had flagged as genuinely strange. The winds do not all move the same direction. On most planets, wind patterns form broad bands that sweep either east or west, depending on latitude, but they generally move in some alignment with the planet's overall rotation. Earth's jet streams, Jupiter's famous stripes, Saturn's hexagonal storm at its north pole, all of these follow some relationship with how the planet spins. Neptune breaks the pattern in a specific way that still does not have a clean explanation. At the equator, Neptune's winds blow westward, meaning they run opposite to the planet's rotation. The planet spins eastward, and the atmosphere at its equator flows the other way, like a river running upstream against the current pulling it. These retrograde equatorial winds are among the fastest on the planet, reaching hundreds of miles per hour in the wrong direction, move toward the poles, and the winds shift. At higher latitudes, the winds switch back and start blowing eastward with the planet's rotation. The atmosphere changes direction depending on where you are standing, and the boundary between those opposing wind systems creates intense shear zones, regions where two different air masses moving in opposite directions meet and grind against each other. On Earth, those kinds of shear zones produce powerful storms. Tornadoes can form where opposing winds meet. Thunderstorms build along boundaries between warm and cold air moving different ways. On Neptune, those shear zones stretch for thousands of miles. Scientists have debated the cause of retrograde equatorial winds since Voyager 2 first measured them in 1989. One idea involves the planet's internal heat distribution. If the deep interior of Neptune generates more heat at certain latitudes, it could create rising columns of warm gas that drive the surface winds in unexpected directions. Another idea involves the planet's magnetic field, which is so unusual that it may be channeling energy through the atmosphere in ways that have no parallel anywhere else in the solar system. The magnetic field on Neptune is tilted 47 degrees away from the planet's rotational axis. For comparison, Earth's magnetic field is tilted about 11 degrees from its spin axis, and that small tilt is enough to make compass navigation slightly complicated. Neptune's tilt is 4 times more severe, which means the magnetic forces guiding particles through the atmosphere are pulling in wildly different directions depending on where you are on the planet. There is also the matter of where the magnetic field comes from. On Earth, the magnetic field is generated by liquid iron churning in the outer core, deep at the center of the planet. Neptune's magnetic field appears to be generated by a thin, electrically conductive layer much closer to the surface, possibly a region of highly pressurized water-ammonia mixture that behaves like a conductor. This off-center, tilted magnetic field may be directly tangled up with the backwards winds, the odd storm behavior, and the disappearing clouds. Everything strange about Neptune might be connected to that one crooked, offset magnetic heart pulsing inside it. And that same heart may be responsible for something nobody expected to see glowing in the sky. While Neptune drags through its 165-year orbit at a crawl, the planet itself is spinning at a startling pace. One full rotation of Neptune takes just 16 hours. 16 hours for an entire planet 4 times wider than Earth to complete one full spin. For comparison, Earth takes 24 hours. Mars takes about 24.5 hours. Even Jupiter, the largest planet in our solar system, takes about 10 hours. Neptune sits at 16 hours, a fast spin for a body this size. And that rotation has a direct effect on almost everything happening in its atmosphere. Fast planetary rotation does something specific. It flattens the planet slightly at the poles and puffs it out at the equator. Earth is slightly wider at its equator than from pole to pole for this exact reason. Neptune is as well, though the difference is subtle. More importantly, a fast spin organizes atmospheric circulation into bands. The faster a planet spins, the more its weather tends to get sorted into east-west stripes rather than more chaotic swirling patterns. Neptune's fast spin is one reason its atmosphere organizes into bands at all, despite the extreme internal heat churning through it from below. The 16-hour day also creates a strange time math that is hard to fully picture. A human standing on Neptune, which is impossible for many reasons, would experience a day that ends in about 16 hours, but they would have to wait 165 Earth years for the seasons to cycle. A single Neptunian season lasts about 40 Earth years. 40 years of the same general seasonal conditions. Assuming seasons on Neptune even follow the patterns scientists expect, which they increasingly do not. Here is something that connects this fast spin to the recent discoveries. Because Neptune's rotational axis is tilted about 28 degrees from vertical, roughly similar to Earth's 23.5-degree tilt, it does experience seasons. During its long orbit, different hemispheres get slightly more sunlight for roughly 40 Earth years at a stretch. Scientists had assumed this seasonal cycle was too weak to drive major changes in the cloud system, given how little sunlight Neptune receives in the first place. The cloud disappearance event of 2023 forced them to reconsider. The clouds vanished right around the time Neptune's southern hemisphere was entering a certain phase of its seasonal cycle. Some scientists now believe the seasonal shift was playing a role, changing the temperature and chemistry of the upper atmosphere just enough to make the clouds vulnerable to the solar event that ultimately stripped them away. A 16-hour spin, a 40-year season, a 165-year orbit, all 3 timescales are layered on top of each other, each one affecting the planet differently, and scientists are only now beginning to map how those layers interact. And within all that churning, within those competing rhythms, something happened to the clouds that no one saw coming. For as long as scientists had been watching Neptune carefully, the clouds were there, bright white streaks of frozen methane cutting across the deep blue face of the planet. You could see them in every high-quality image taken over decades of observation. They were as reliable as anything gets in planetary science. Researchers tracked them, measured their altitude, used them to calculate wind speeds. The clouds were a constant, Then, in images captured around 2023, they were almost completely gone. Astronomers at the Keck Observatory in Hawaii first noticed the change. They had been systematically photographing Neptune for years, building up a long record of the planet's cloud coverage. When they compared recent images to older ones, the difference was jarring. The white streaks had faded, the bright bands had thinned. In some parts of the planet, the cloud coverage had dropped by nearly all of what had been there before. Other observatories confirmed it. The Hubble Space Telescope captured the same picture. The clouds on Neptune had essentially vanished. Scientists immediately started asking why. The methane clouds on Neptune form when methane gas rises to the upper atmosphere, where temperatures are cold enough to freeze it into ice crystals. For those clouds to disappear, something had to either prevent the methane from rising, strip the ice crystals away before they could form into visible bands, or change the chemistry of the upper atmosphere so completely that the freezing process broke down. A team of scientists went back through decades of observational data looking for a pattern. They found one. The cloudiness of Neptune's atmosphere tracked closely with the 11-year solar cycle. The solar cycle is the regular rhythm in which the sun's activity ramps up and then quiets down every 11 years. At peak solar activity, the sun produces more ultraviolet radiation, the high-energy light that can break apart molecules. When the team plotted Neptune's cloud coverage against the solar activity record, the correlation was striking. More solar ultraviolet radiation arriving at Neptune meant fewer clouds, roughly 2 years later. The 2-year lag matched the time it would take for the chemical effects of the increased radiation to work their way through the upper atmosphere. The sun, from nearly 3 billion miles away, was controlling the weather on Neptune. This was surprising on a level that is hard to overstate. Scientists had assumed Neptune was so far from the sun that solar activity would have almost no effect on it. The planet receives a tiny fraction of the sunlight that Earth gets. The idea that the 11-year solar cycle would show up clearly in Neptune's cloud patterns across billions of miles of space required a complete rethinking of how much influence our star has over the outer solar system. And the clouds were just the beginning. Something else was glowing on Neptune that year, something that should have been impossible, and it took the most powerful telescope ever built to catch it. The connection between the Sun and Neptune's clouds is more layered than it first appears. When scientists confirmed the link between solar ultraviolet radiation and Neptune's cloud disappearance, they had to figure out the actual mechanism. How does ultraviolet light from the Sun, arriving at Neptune as a whisper compared to what Earth receives, still manage to destroy cloud formations across an entire planet? The answer lies in photochemistry. Ultraviolet light carries enough energy to break chemical bonds. On Earth, this is why you get a sunburn. Ultraviolet radiation breaks apart molecules in your skin cells, damaging the cellular structure. In Neptune's upper atmosphere, the same process targets the methane and haze particles that seed cloud formation. When ultraviolet radiation hits the upper atmosphere of Neptune, it breaks apart methane molecules. The fragments then react with other chemicals present in the atmosphere, producing new compounds and altering the chemistry of the region where clouds form. If enough methane is broken apart, there are fewer molecules available to freeze into ice crystals, and the cloud layers thin out. The key detail is the 2-year lag. The radiation hits Neptune, but the chemical changes take time to work their way through the atmosphere. The broken methane molecules need time to react. The altered chemistry needs time to propagate down to the altitudes where clouds actually form. Scientists estimate this process takes roughly 2 Earth years from the time the radiation arrives to when the change in cloud coverage becomes visible. This 2-year lag was the smoking gun. When the research team plotted the timing, the solar cycle peak matched the cloud disappearance with exactly the right delay. The match was so precise that it essentially ruled out coincidence. The sun was the cause, and the mechanism was ultraviolet photochemistry playing out across billions of miles. What makes this discovery even more important is what it tells scientists about other planets in the outer solar system. Uranus sits closer to the Sun than Neptune and has a similar atmosphere, If solar ultraviolet radiation is powerful enough to visibly alter Neptune's cloud chemistry, it must also be affecting Uranus in ways that scientists have not fully measured yet. The same process likely plays out across every ice giant in our solar system, and possibly even in the atmospheres of large moons. The Sun's reach is longer than anyone assumed, but there is a complication. The solar cycle link explains the cloud disappearance. It does not explain everything else. The storms on Neptune do not follow the solar cycle. The internal heat output does not follow it either. The auroras that scientists recently discovered were photographed right around the time the clouds were gone, but their cause has nothing to do with methane chemistry. The auroras on Neptune have their own explanation, and that explanation requires a look at one of the strangest magnetic fields in the entire solar system. Because what the James Webb Space Telescope found glowing in Neptune's sky did not belong in the places where it was found. Something was lighting up the wrong parts of the planet. Auroras are supposed to follow the rules. On Earth, the northern and southern lights form because charged particles from the sun stream into our atmosphere along magnetic field lines. Those field lines connect at the magnetic poles, so auroras glow near the poles. Always. The rule is simple. Magnetic field lines guide particles to the poles. Poles get the light show. Jupiter follows the same rule. Saturn follows it. The pattern holds across every planet scientists had studied in detail. Then the James Webb Space Telescope turned its infrared sensors toward Neptune. The images came back, showing auroras, but they were not near Neptune's poles. They were glowing at the mid-latitudes, the regions equivalent to somewhere around the latitude of Florida or Spain on Earth, right in the middle of the planet, nowhere near where the magnetic poles sit. The scientific team stared at those images for a long time. The discovery was published in 2025, and it immediately raised questions that nobody had clean answers to. If auroras form where magnetic field lines channel particles into the atmosphere, and Neptune's auroras are forming at the mid-latitudes, then Neptune's magnetic field lines must be doing something completely unexpected. To understand why, you need to know how far off Neptune's magnetic field really is. On Earth, the magnetic poles sit close to the geographic poles. The axis of Earth's magnetic field is tilted only about 11 degrees from the rotational axis. Particles from the Sun follow the field lines down toward the geographic poles, and that is where the lights appear. Neptune's magnetic field axis is tilted 47 degrees from its rotational axis, and the field itself is not generated at the center of the planet. It is offset, generated somewhere closer to the surface in one of the outer shells of the planet. This means the magnetic field of Neptune is lopsided, stronger on one side than the other, and the field lines do not form the clean, organized funnels that guide auroras on Earth or Jupiter. The field lines on Neptune twist and fold in patterns that have no real equivalent anywhere in the solar system. When solar wind particles hit Neptune's magnetosphere, the lopsided field channels them into the atmosphere in unpredictable locations. The mid-latitude auroras are evidence of a magnetic system so complex that even the best current models cannot fully predict where the light will appear. There is another layer here that has scientists actively debating. On Earth, auroras light up the visible spectrum. You see green, pink, and red with your naked eye. Neptune's recently detected auroras glow in the infrared spectrum, meaning they are invisible to human eyes. Only a telescope sensitive to infrared light, like the James Webb Space Telescope, could catch them. This raises an important question. Were the auroras always there, glowing invisibly, and scientists simply lacked the instruments to find them? Or are they a recent development driven by changing conditions in the atmosphere? The answer changes how scientists interpret everything else they have observed about Neptune over the past several decades. And it feeds directly into the larger mystery of that twisted magnetic field and where it actually comes from. Every magnetic field in the solar system has rules. Even the complicated ones follow patterns scientists can describe and predict. Neptune breaks those patterns at almost every level. Start with the basics. A planet's magnetic field is usually generated in its deep interior, where some combination of liquid metal, pressurized fluid, or electrically conductive material moves and churns. On Earth, liquid iron in the outer core swirls under convection, driven by the heat escaping from the even hotter inner core. That swirling liquid metal creates electric currents, and those currents generate a magnetic field. The whole process is centered at the planet's core. Neptune's magnetic field appears to be generated in a thin shell of material far from the center. Scientists believe the source is likely a layer of superionic water, a bizarre state of matter where oxygen atoms lock into a solid lattice while hydrogen ions flow freely through it like a liquid. This superionic layer conducts electricity, and when it circulates, it generates a magnetic field. Because this generating layer is far from the center and forms an irregular shell rather than a symmetrical core, the field it produces is wildly uneven. It is tilted 47 degrees from the rotational axis. It is offset from the geometric center of the planet by a significant distance, and it changes strength and direction depending on which part of the planet you are measuring from. The practical result is that Neptune's magnetic environment is constantly shifting. As the planet rotates in 16 hours, the lopsided field sweeps through space like a wobbling top. The magnetosphere, the region of space controlled by Neptune's magnetic field, pulses and shifts with every rotation. Solar wind particles hitting this magnetosphere do not encounter a clean, organized shield. They encounter a tumbling, uneven barrier that funnels particles into unpredictable locations and creates auroras at mid-latitudes instead of poles. This also has implications for Neptune's moons. Triton, Neptune's largest moon, orbits deep inside this chaotic magnetic environment. Every time Triton completes an orbit, it passes through regions of wildly different field strength. The interaction between Triton's thin atmosphere and Neptune's pulsing magnetic field creates a continuous exchange of particles that scientists are only beginning to model, and Triton's orbit is unusual in its own right, in ways that have nothing to do with magnetism. Scientists know that most moons in the solar system formed from the same disk of material that built their parent planet, orbiting in the same direction the planet rotates. Triton does the opposite. It orbits Neptune backwards, and that single fact blows open an entirely different chapter in the story of how this system came to be. But first, there is a storm that needs addressing, a storm the size of an entire planet, a storm that appeared, dominated the face of Neptune for years, and then simply ceased to exist. When Voyager 2 arrived at Neptune on August 25, 1989, the scientists tracking the probe had been waiting 12 years for this moment. Voyager 2 had already visited Jupiter and Saturn and Uranus. It was fast, and it was precise, and it was carrying instruments that could capture images of a quality never seen before at this distance from Earth. The team at NASA's Jet Propulsion Laboratory in Pasadena, California, had been calculating the flyby trajectory for years. What they saw in the first close images made several of them stop talking mid-sentence. Sitting in Neptune's southern hemisphere was a storm, a massive, rotating anticyclone, dark, elliptical, and unmistakable. It stretched roughly the width of an entire planet, Earth. The storm was the size of Earth, spinning in Neptune's blue atmosphere like a bruise on the face of the planet. They named it the Great Dark Spot. The comparison to Jupiter's Great Red Spot was immediate. Jupiter has hosted its Great Red Spot, a giant anticyclone, for at least 350 years of recorded observation. Some estimates put it far older. Scientists assumed the Great Dark Spot on Neptune would follow the same pattern, a permanent feature, a stable storm locked into the atmosphere by the same forces that keep Jupiter's storm alive. The Great Dark Spot had features that Voyager 2 captured in remarkable detail. Bright white clouds of frozen methane formed along its southern edge, scooched along by the fierce winds, then stretched and swept upward over the storm's boundary in a pattern scientists called cirrus. The scooter, a smaller bright cloud formation nearby, raced around Neptune at a different speed than the Great Dark Spot, lapping the larger storm every few days. Winds around the edges of the Great Dark Spot clocked in at over 900 miles per hour. The storm showed clear internal structure, with a dark core and rotating bands that reflected the intensity of the circulation beneath. Scientists estimated the storm had been there long enough to become fully organized and stable, meaning it had probably been spinning for at least years, possibly much longer, before Voyager 2 arrived. Then Voyager 2 left. The spacecraft completed its flyby and continued on its trajectory out of the solar system. The Neptune system went back to being observed only by distant telescopes. 5 years later, in 1994, the Hubble Space Telescope turned its gaze toward Neptune and captured something that genuinely puzzled the science team. The Great Dark Spot was gone. No debris, no smaller storms left in its wake. The southern hemisphere, where the massive anticyclone had been spinning, was clear. A storm the size of Earth had simply stopped existing. That discovery changed everything scientists thought they knew about Neptune's weather system. And it was only the first disappearance. When the Hubble Space Telescope confirmed that the Great Dark Spot had disappeared, the immediate reaction among planetary scientists was disbelief, followed by a very specific kind of scientific frustration. They had only one data point. Voyager 2 had photographed the storm in August of 1989. The Hubble images from 1994 showed it gone. That left a 5-year window during which the storm had collapsed, and no close-up data to explain how. From Earth, even with Hubble, Neptune is small. Details that Voyager 2 could resolve in stunning clarity became tiny smudges at this distance. Scientists could confirm the storm was absent, but they could not observe its final days, could not watch it weaken, could not see whether it died gradually or suddenly. What they could do was look more carefully at the rest of the planet, and what they found was not emptiness, it was replacement. By the mid-1990s, Hubble images showed a new dark spot forming in Neptune's northern hemisphere. Roughly similar in size to the original, similarly organized, similarly wrapped in bright white methane clouds along its edges, a new great dark spot in a different place. Then that one faded too. Over the following decades, Hubble and ground-based observatories documented a series of dark spots forming and dissipating on Neptune. They appeared in different hemispheres, at different latitudes, sometimes overlapping in timing with each other. The pattern that emerged was clear. Neptune does not sustain one permanent giant storm. It generates them regularly, allows them to develop and grow, and then the atmosphere absorbs them back. This is fundamentally different from Jupiter. Jupiter's Great Red Spot has maintained itself for centuries because Jupiter's atmosphere provides a specific set of stable conditions that lock the storm in place. Jupiter receives enough solar energy to maintain consistent temperature gradients, and its interior heat distribution is relatively uniform. These factors together create a kind of atmospheric trap that keeps the storm alive. Neptune's interior heat is less organized. It varies across the planet and changes over time, driven by processes deep inside the planet that scientists do not yet fully understand. When the internal heat distribution shifts, the atmospheric conditions that support a given storm can disappear. The storm finds itself sitting in an environment that no longer matches the conditions it needs, and it dissolves. Scientists now believe Neptune's dark spots form when deep interior dynamics push the right combination of heat and pressure up into the atmosphere. The spots live for months or years, sometimes growing to enormous sizes, and then the interior conditions shift again, and the support beneath the storm collapses. The storms are symptoms. The real weather engine is underground, and that underground engine is doing something even more extraordinary than powering hurricanes the size of continents. Something is happening in the deep interior of Neptune that produces a phenomenon straight out of science fiction. Except the laboratory has already recreated it, and it rains down slowly, crystal by crystal, toward the core. Neptune sits so far from the sun that the sunlight arriving there carries almost no warmth. If you could stand in Neptune's atmosphere and hold up a solar panel identical to the ones on Earth's most powerful satellites, the energy it captured would be roughly 900 times less than the same panel would collect in Earth's orbit. The Sun is a dim, cold-looking star from out there. It gives almost no usable heat to the atmosphere. Yet Neptune's atmosphere is one of the most violent in the solar system. The storms, the winds, the cloud cycles, the disappearing dark spots, none of it is powered by the Sunday. The engine driving all of it sits beneath the cloud tops, buried deep inside the planet, invisible from outside. Neptune radiates more than twice the energy back into space than it ever receives from the Sunday. The planet is generating heat internally and sending it outward constantly, a slow leak of energy from somewhere inside its core. On Earth, the concept of a planet warming itself from the inside is familiar. Earth's interior is hot from two sources: leftover heat from the planet's formation billions of years ago, and ongoing heat from radioactive decay in the rocks of the mantle and core. That internal heat drives volcanoes and tectonic plates, but it does not significantly heat Earth's atmosphere. The Sun does that job. Neptune has no tectonic plates, no volcanoes breaking through a solid crust. The heat it generates gets conducted upward through the thick layers of pressurized fluid inside the planet until it reaches the atmosphere, where it escapes as infrared radiation. This outward flow of heat creates the temperature differences that drive Neptune's enormous winds. When warm gas rises through the atmosphere, it displaces cooler gas, creating circulation patterns. On a fast-spinning planet, those circulation patterns stretch out into the east-west bands scientists observe. The boundary zones between rising warm gas and sinking cool gas become the shear regions where the most violent wind speeds develop. The 1,200 mile-per-hour winds are the atmosphere trying to balance the heat flowing out of the planet. The planet is essentially exhaling energy, and the exhale comes out as the fastest sustained winds in the solar system. The dark spots form within this system because the internal heat does not rise uniformly. Some regions of the deep interior push more heat upward than others. When an unusually hot column of gas rises through the atmosphere, it disrupts the surrounding wind patterns and triggers a rotation. The dark spot is the visible signature of that hot column punching upward from below. When the hot column cools or shifts, the dark spot loses its support and dissolves. This mechanism, storms driven from within rather than from above, makes Neptune fundamentally different from every planet in the inner solar system. And it raises a question that scientists have been arguing over for decades. Where is all that internal heat coming from? One answer is elegant. One answer is extraordinary. One answer involves carbon atoms being crushed into crystals and falling slowly through thousands of miles of pressurized fluid in a rain that has been falling continuously for billions of years. In the 1980s, a physicist named Marvin Ross proposed something that most scientists initially considered too extreme to take seriously. He suggested that deep inside the ice giants of our solar system, it rains diamonds. The idea came from thinking carefully about what happens to methane under extreme pressure. Methane is a simple molecule, one carbon atom connected to 4 hydrogen atoms. At the pressures and temperatures that exist in the deep interior of Neptune, something happens to those molecules that cannot happen anywhere on the surface of any planet. They break apart. The pressures at depth inside Neptune reach millions of times the pressure of Earth's atmosphere at sea level. At those pressures, the hydrogen atoms in methane get forced away from the carbon atoms. The carbon atoms are left free, and under those same crushing pressures, they bond together. When carbon bonds to other carbon atoms under extreme pressure, it forms diamond. These microscopic diamonds then sink. The fluid mantle of Neptune, a thick, pressurized mix of water, ammonia, and other compounds, is dense enough to let solid objects drift downward slowly over time. The diamonds do not drop like stones in air. They descend gradually, sinking through thousands of miles of pressurized fluid, carrying energy with them as they go. The friction of all those crystals moving through the fluid generates heat. For decades, this was a compelling hypothesis, but nobody could test it in a real laboratory because recreating the interior conditions of Neptune is nearly impossible at anything larger than a microscopic scale. In 2017, a team of scientists at the SLAC National Accelerator Laboratory in California managed to do it. They used a high-powered laser to compress a thin layer of polystyrene, a plastic material that contains carbon and hydrogen in a similar ratio to methane. The laser created a shockwave that generated pressures and temperatures comparable to the conditions roughly 10,000 miles deep inside Neptune. Using X-ray imaging, they watched in real time. The carbon atoms separated from the hydrogen atoms and formed tiny diamond structures within the compressed material. The experiment worked. Diamond rain inside Neptune changed from a hypothesis to a phenomenon that has been reproduced in a controlled setting. The diamonds forming inside Neptune are estimated to be extremely small, perhaps no larger than a piece of sand, though scientists believe that as they sink deeper and the conditions change, they could potentially grow much larger over time. Some researchers have speculated that near the very core of Neptune, large diamond formations might accumulate. A layer of diamond sitting at the center of the planet, built up over billions of years of continuous precipitation from above. This is a place where scientific evidence and genuine wonder overlap, and the diamond rain may be doing something even more consequential than creating beautiful crystals in the deep dark. It may be the reason Neptune glows. Every planet in the solar system receives energy from the sun and radiates some of it back as heat. The balance is usually straightforward. A planet takes in a certain amount of solar energy and eventually releases a roughly equal amount. The farther a planet sits from the sun, the less energy it receives and the less it radiates. Neptune does not follow this rule. Scientists measuring the heat coming off Neptune found that the planet radiates about 2.6 times more energy than it receives from the Sunday. Neptune absorbs a tiny trickle of solar warmth from billions of miles away, and then releases significantly more than twice that amount back into space. The numbers do not balance. The planet is producing its own energy on a substantial scale. This excess heat output is one of the oldest unsolved problems in Neptune science. It was measured decades ago and has been consistently confirmed. The question of where that extra energy comes from has generated significant debate. The diamond rain hypothesis offers one answer. When diamonds form in the deep interior and begin sinking through the fluid mantle, they release gravitational potential energy. This is the same kind of energy released when any object falls, converted from potential to kinetic energy, and then, through friction with the surrounding fluid, into heat. Billions of tiny diamonds, continuously sinking through thousands of miles of fluid, represent a continuous and very large energy source. Scientists who favor this explanation calculate that the rate of diamond formation and descent could plausibly account for a meaningful fraction of Neptune's excess heat output. The process has been running since the early solar system, billions of years ago, and shows no sign of stopping. As long as methane exists in the deep interior and the pressures remain high enough to break it apart, the diamond rain continues and the heat continues. This would mean Neptune is essentially running on a geological engine powered by crystallography, carbon atoms forming diamonds, sinking, generating heat, driving the internal temperature that drives the winds that drive the storms. A chain of processes connecting the chemistry of a simple molecule all the way up to the 1,200 mile per hour winds, visible from telescopes billions of miles away. The competing explanation is simpler and in some ways more troubling. Some scientists argue that Neptune is simply releasing leftover heat from its own formation. When the planet assembled itself from billions of rocky and icy chunks roughly 4.5 billion years ago, the energy from all those collisions converted into heat. A planet as large as Neptune would have retained enormous amounts of that primordial heat and it could be slowly bleeding outward over the age of the solar system, still releasing the warmth from the violence of its own birth. Under this model, diamond rain may still occur, but it plays a smaller role in the heat budget. The planet would eventually cool as the formation heat runs out, though that process would take billions more years. The honest answer is that scientists do not yet know which explanation carries more weight. What they do know is that the interior of Neptune is far more complicated than any early model predicted, and the latest measurements of that interior have forced a complete revision of how the planet was built in the first place. For most of planetary science history, Neptune's interior looked a certain way on paper: a small rocky core at the center, roughly the size of Earth. Surrounding that core, a vast ocean of hot pressurized fluid made of water, ammonia, and methane, all mixed together under conditions so extreme. The fluid behaves more like a thick syrup than anything you would recognize. Above that, the gaseous atmosphere stretching upward to the cloud tops, clean, layered, simple. Then gravitational measurements started coming in that did not match the model. Scientists measure a planet's internal structure by studying its gravitational field with extreme precision. As a spacecraft passes near a planet, the planet's gravity tugs on the craft in ways that reveal the distribution of mass inside. Regions of higher density pull harder, regions of lower density pull less. By mapping those variations, scientists can build a picture of what the inside looks like without ever going there. Recent measurements of Neptune's gravitational field produced results that required the standard model to be thrown out and rebuilt. The data suggested that Neptune contains significantly more rock and heavy metals distributed through its interior than anyone had calculated. The interior appears to be a mixture of rock, ice, and pressurized fluid blended together rather than separated into clean, distinct layers. The rocky material does not sit neatly at the center. It extends outward through much of the planet's interior, mixed into the surrounding fluid in proportions that earlier models simply did not account for. This changes the picture of Neptune's interior from a layered cake into something more like a dense, poorly mixed batter. Rock and ice and fluid all together, under pressures that transform each material into states that do not exist anywhere on Earth. The revised interior model also shifts how scientists think about the planet's density. Neptune is denser than Uranus, despite both planets being classified as ice giants with similar compositions on paper. For years, scientists attributed this difference to subtle variations in their atmospheric chemistry. The new rock-heavy interior model provides a more satisfying explanation. Neptune accumulated more rocky material, and that rock is still there, packed through the interior, making the whole planet heavier than expected. The superionic water layer that scientists believe generates the magnetic field fits differently into this new picture as well. If the interior is more thoroughly mixed with rock, the exact depth and thickness of the superionic layer changes. This affects predictions about the magnetic field's strength, its offset from the center, and the reason it tilts 47 degrees from the rotational axis. Every revision to the interior model ripples outward into every other part of Neptune science, and the reason Neptune ended up with so much rocky material inside it points back to the very beginning of the solar system, when the outer planets were still being assembled from the cloud of dust and rock that surrounded the young Sunday. What Neptune consumed during those first chaotic millions of years shaped everything it is today. 4.5 billion years ago, the solar system was not a collection of orderly planets circling a stable star. It was a demolition derby. Billions of rocky chunks, called planetesimals, were hurtling through the early solar system, crashing into each other, merging, fragmenting, and rebuilding in a continuous, violent process. The regions beyond the frost line, the distance from the sun where temperatures dropped cold enough for water and ammonia to freeze, were rich with these icy, rocky bodies. This is the region where Neptune formed. The revised interior model suggests Neptune was an unusually aggressive consumer during this period. The planet did not simply gather the nearest available material and stop growing. Gravitational simulations based on the new density measurements suggest Neptune swept through a much larger region of the early solar system than previously modeled, pulling in rocky planetesimals from a wide range of distances. Each collision added mass, compressed the interior further, and generated enormous heat. This aggressive early growth explains why Neptune ended up so rocky compared to what the older models predicted. It also raises a point about the solar system's overall architecture that planetary scientists find genuinely unsettling. The four giant planets, Jupiter, Saturn, Uranus, and Neptune, are arranged in a specific order of distance from the Sunday. But that order may not be the order in which they formed, and it may not be the order they were always in. A model developed by a group of planetary scientists called the Grand Tack hypothesis, and later the Nice model, proposed that the giant planets migrated significantly during the early solar system, moving inward and outward as they traded gravitational energy with each other and with the disk of debris surrounding them. Under these migration models, Neptune may have formed closer to the Sun than it currently sits and drifted outward over millions of years to its current position. As it moved, it would have swept through different populations of planetesimals, consuming rocky material from regions that no longer exist as distinct structures today. The high rock content in Neptune's interior may be a record of that ancient migration, a geological memory of where the planet traveled before it settled into its current orbit. This matters for understanding planetary systems beyond our own. Astronomers have found ice giants orbiting other stars. Some of them orbit in positions and with densities that do not match what scientists expected based on the old Neptune model. The revised understanding of how Neptune built itself, migrating, sweeping, consuming, could explain why ice giants in other solar systems look different from what the simple formation models predicted. Neptune is not just a planet at the edge of our solar system, it is a data point for understanding how planets form everywhere in the universe. And the moons it carries with it carry their own extraordinary stories about where they came from, starting with the one that orbits the wrong way. Every large moon in the solar system formed from the same process. When a planet is still young and surrounded by a disk of gas and debris, material clumps together within that disk and gradually assembles into moons. Because the disk spins in the same direction as the planet, the moons that form from it orbit in the same direction too. This is the rule. It applies to Earth's moon, to Jupiter's 4 large Galilean moons, to Saturn's Titan, to most large moons throughout the solar system. Triton orbits Neptune in the opposite direction. This single fact tells scientists everything they need to know about where Triton came from. It was not born alongside Neptune. It was captured. Triton originated somewhere else in the outer solar system, most likely in the region beyond Neptune's orbit that is packed with icy objects called the Kuiper Belt. Triton was once one of those objects, a large, icy body orbiting the Sun on its own path. Then, at some point billions of years ago, it came too close to Neptune. Neptune's gravity grabbed it. Capture events are violent and complicated. A passing object does not simply get grabbed and settle into a nice circular orbit. To be permanently captured, Triton had to lose enough energy to stop being flung back out into space. Scientists believe this happened because Triton interacted with the gas and debris still surrounding the young Neptune, and those interactions bled off enough of Triton's orbital energy to trap it. The result was a highly stretched, tilted orbit that slowly circularized over hundreds of millions of years through tidal interactions with Neptune. But the consequences of the capture were catastrophic for whatever moons Neptune had before. When Triton arrived on its chaotic incoming trajectory, its gravitational influence would have disrupted any moons already orbiting Neptune in the normal direction. Simulations show that a Triton mass object on a retrograde capture path would destabilize a large fraction of a pre-existing moon system, sending those original moons crashing into each other or getting flung out of the Neptune system entirely. The small, irregular moons that orbit Neptune today may be fragments left over from that ancient collision cascade. Triton is also special in another way that has nothing to do with its orbit. It is one of the few moons in the solar system known to be geologically active. Its surface is young by solar system standards, refreshed by ongoing processes that resurface the ice. And from its south polar region, something is erupting. Geysers of nitrogen gas shoot upward from cracks in Triton's icy surface, carrying dark particles of dust miles into the thin atmosphere, before the plumes drift downward and leave dark streaks on the ice. But Triton's most dramatic future is not what it is doing now. It is what Neptune's gravity is slowly, patiently doing to it. Triton's surface sits at minus 390 degrees Fahrenheit. That is the coldest surface temperature of any measured body in the entire solar system. Cold enough that nitrogen, the gas that makes up most of Earth's atmosphere, freezes into a solid layer of pink and white ice across Triton's terrain. The surface is almost completely flat in many regions, smoothed by repeated flooding and refreezing over billions of years. It looks, in some images, like the skin of a cantaloupe, and from that frozen surface, geysers erupt. Voyager 2 discovered the geysers in 1989 during its brief flyby. Scientists spotted dark streaks on Triton's southern polar cap stretching downwind for miles, the leftover marks of plumes that had risen and drifted in the thin atmosphere before settling back down. Then Voyager 2's cameras caught two active geysers in the process of erupting, shooting dark columns of nitrogen gas and dust particles upward for roughly 5 miles before the plumes spread horizontally in the nitrogen wind. The energy source behind these geysers was initially puzzling. Triton receives so little sunlight at its distance from the sun that the warming effect should be negligible, but the nitrogen ice on Triton's south polar cap is transparent. Sunlight passes through the top layers of ice and gets absorbed by the darker material beneath, converting to heat in a greenhouse effect operating at microscopic scale. The trapped heat warms the nitrogen below the surface until pressure builds up enough to blast through cracks in the overlying ice. The result is a geyser powered by one of the weakest sunlight sources in the solar system, operating at temperatures that would instantly freeze any liquid water from Earth. These geysers matter beyond being a striking visual. They are evidence that Triton has an active surface. The dark material the geysers eject contains organic compounds, complex carbon-based molecules that were present when Triton formed in the outer solar system. Studying what the geysers bring to the surface could give scientists a window into the chemistry of the original Kuiper Belt objects, the primordial building blocks from the edge of our solar system. Triton is also suspected of harboring a liquid ocean beneath its icy crust. The tidal forces from Neptune's gravity flex Triton's interior as it orbits, generating heat from friction. Combined with the leftover heat from Triton's capture billions of years ago, this tidal heating may keep a layer of water liquid far below the surface. If confirmed, Triton would join Europa, Enceladus, and a growing list of outer solar system bodies where liquid water may exist in the complete absence of sunlight. The possibility of a subsurface ocean on a moon orbiting in the wrong direction, erupting geysers from a surface colder than anything on Earth, is the kind of discovery that redefines where scientists should be looking for conditions that could support life. And Triton's story has one more chapter that has not been written yet. A chapter that will play out billions of years from now, when Neptune finishes what it started when it first captured this wandering moon. Every orbit Triton completes around Neptune is slightly smaller than the last. The difference is tiny, unmeasurable in a human lifetime. But it is consistent, it is confirmed, and it is relentless. Triton is falling toward Neptune in a death spiral that has been running since the moon was first captured, and it will end in one of the most spectacular events our solar system will ever produce. The reason comes down to tidal forces. When Triton was first captured and settled into its backward orbit, it was orbiting in the opposite direction to Neptune's rotation. This retrograde orbit puts Triton in a specific tidal relationship with the planet, where the interaction between the two bodies drains energy from Triton's orbit rather than adding to it. On Earth's moon, tidal interactions are slowly pushing the moon outward, increasing its orbital distance by about 1.5 inches per year. Triton experiences the opposite effect because of its retrograde direction. Tidal interactions pull it inward. The result is a moon on a death countdown. Scientists calculate that in roughly 3.5 billion years, Triton will cross a boundary called the Roche limit. The Roche limit is the distance from a planet at which the planet's tidal forces become stronger than the gravitational forces holding a moon together. Inside that boundary, the planet essentially pulls the moon apart. When Triton crosses the Roche limit, Neptune's gravity will begin tearing the moon into pieces. The outer parts of Triton will be peeled away first, sending debris streaming into orbit around Neptune. Over millions of years following the initial breakup, this debris will spread around the planet in a ring. The ring that eventually forms from Triton's destruction will be extraordinary. Triton is roughly 1,600 miles across. It contains an enormous amount of mass, far more than the material making up Saturn's rings. Scientists estimate the ring system that forms from Triton's breakup could be significantly larger and more massive than Saturn's rings, potentially visible across interplanetary distances. This will happen in 3.5 billion years. The sun will still be burning, the solar system will still be intact. Triton will become Neptune's most spectacular feature, a ring system grander than anything existing in the solar system today. What is sitting in Neptune's ring system right now is a much more modest structure, but even the current rings hide something that took decades to explain, because Neptune's rings do not form clean, continuous circles around the planet. They clump, they gather into arcs, and arcs of dust and debris in a ring system should not be stable. The physics say they should spread out and disperse within years. Something is holding them together, and what that something is connects directly back to the small, irregular moons orbiting close to the rings. Saturn's rings are one of the most recognizable images in all of science. Bright, wide, dramatic arcs of ice and rock catching sunlight from millions of miles away. Even a small amateur telescope shows them clearly on a good night. Neptune has rings too. You need a very powerful telescope just to confirm they exist. Neptune's rings are thin, dark, and made of materials so small and so low in reflectivity that they absorb most of the light that hits them instead of bouncing it back. The particles making up the rings are thought to be coated in organic compounds similar to the material found on dark comets and Kuiper belt objects, compounds that form over billions of years of exposure to radiation and slowly turn the surface of ice and rock into a dark, carbon-rich crust. The rings are named. The outermost major ring is called Adams. Closer in sits the Leverrier ring, and closer still are the Galley ring and a diffuse inner ring called Lassell. These names honor the scientists involved in Neptune's discovery, a tradition of recognition embedded in the planet's geography. But the Adams ring is the one that defied explanation for years. Instead of being spread evenly around the planet in a uniform band, the Adams ring has 5 distinct, bright clumps embedded in it, regions where the material is noticeably denser than the rest of the ring. These clumps are called arcs. The most prominent arcs have been given names: Courage, Liberty, Egalite, and Fraternite. The problem with arcs is that they should not last. In orbital mechanics, particles in a ring orbit the planet at slightly different speeds depending on how close they are to the planet. This difference in speed, called Keplerian shear, gradually spreads material out. A clump of particles should smear itself into an even band within a matter of decades. The arcs in Neptune's Adams ring have been observed and confirmed over decades of observation. They are still there. Something is preventing the shear from dispersing them. The leading explanation involves a small moon called Galatea. Galatea orbits just inside the Adams ring, and its gravitational influence creates a pattern of resonances within the ring, specific orbital positions where the gravitational tugs from Galatea and Neptune combine in a way that creates stable pockets. Particles that drift into these pockets get nudged back into place. Particles outside the pockets drift away. The result is a concentration of material held in place by the combined gravitational landscape of the moon and the planet. Galatea is essentially herding the arc particles, preventing them from spreading, acting as a shepherd for the ring clumps. This shepherd moon mechanism was predicted mathematically before Galatea was discovered. Scientists knew something had to be keeping the arcs together and calculated roughly where the object responsible would have to be. When Voyager 2 arrived and catalogued Neptune's inner moons, Galatea was right where the math said it had to be. Math finding the unseen before the telescope does. The same trick that found Neptune itself. And in 2013, that same kind of careful re-examination of old telescope images revealed something else hiding in plain sight, even closer to the rings. Before reaching the hidden moon discovered in old Hubble images, there is one more moon in Neptune's collection that deserves its own moment. Its name is Nereid, and its orbit is the most extreme of any confirmed moon in the solar system. Most moons orbit their planets in roughly circular paths. Even the highly elliptical orbits of some irregular moons, moons captured rather than formed in place, stay within a general range of distances. Earth's moon swings between about 225,000 miles and 252,000 miles from Earth across its orbit. That variation is less than 15% of the average distance. Nereid swings between roughly 5,000 miles and 6 million miles from Neptune in a single orbit. 5,000 miles at its closest, 6 million miles at its farthest. In one orbit, Nereid covers a range of distance that would span almost the entire width of the inner solar system if you laid it flat. The variation in its distance is roughly 1,200 times greater than the variation in Earth's moon's orbit. Nereid is not so much a moon gently circling Neptune, as it is an object that Neptune is barely managing to keep from flying away. A single Nereid orbit takes about 360 Earth days, almost exactly one Earth year. So every year, this moon swings from a distance where it could see Neptune's cloud details to a distance where Neptune is barely more than a bright star in its sky. The extreme orbit is almost certainly the result of the same ancient catastrophe that brought Triton into the Neptune system. When Triton arrived billions of years ago on its capture trajectory, the disruption to the existing moon system sent objects scattering in all directions. Nereid was likely a normal moon before the capture event, orbiting in a stable, roughly circular path. The gravitational chaos of Triton's arrival kicked Nereid into the wild, stretched orbit it still follows today. Nereid was discovered in 1949 by astronomer Gerard Kuiper, the same scientist whose name is attached to the Kuiper belt beyond Neptune's orbit. At the time, it was only the second moon of Neptune known to science. Triton had been found just 17 days after Neptune's discovery in 1846. Nereid came over a century later. For decades after Nereid's discovery, scientists knew Neptune had exactly 2 moons. Voyager 2 changed that dramatically in 1989, discovering 5 additional inner moons during its brief flyby. Then Hubble found more through careful, long-exposure photography. By 2013, the count had reached 13 confirmed moons, and then someone looked more carefully at images that had already been taken years before, and found one more hiding in the light scatter from the rings. In 2013, a scientist named Mark Showalter was working with archival images captured by the Hubble Space Telescope between 2000 and 2009. These were images that had already been analyzed. Scientists had gone through them looking for moons and had found what they expected to find. The images were considered thoroughly examined and filed away. Showalter was looking at the images for a different purpose, studying the structure of Neptune's rings. To do this, he used a technique that involves stacking multiple images on top of each other and adjusting for the orbital motion of the rings, a method that enhances faint features by averaging out random noise. He was looking for ring structure. Instead, he found a tiny dot moving in a path that was unmistakably orbital. The dot was so close to the Adam's ring that it was sitting in the bright scatter of light from the ring itself, which is why previous searches had missed it. The ring's glow had washed out the faint signal of the moon, hiding it in plain sight across 9 years of observations. Showalter named the new moon Hippocamp, after the sea creature from Greek mythology that is half horse and half fish. Hippocamp is tiny, roughly 21 miles across. That is smaller than many major cities. At that size, it is one of the smallest moons ever confirmed in the outer solar system, too small to be pulled into a spherical shape by its own gravity. It tumbles through its orbit as an irregular lump of dark, heavily cratered ice. The location of Hippocamp is what caught scientists' attention most. It orbits extremely close to a larger moon called Proteus. The two moons are so close in orbital distance that their history is almost certainly connected. Proteus is significantly larger than Hippocamp, roughly 270 miles across, and it carries a large impact crater on its surface called Pharos. The crater is enormous relative to Proteus's size, the kind of impact that would have shattered a smaller object. Scientists think Hippocamp formed from the debris of that impact. When the object that created Pharos hit Proteus billions of years ago, it blasted material off Proteus's surface. Most of that material eventually fell back onto Proteus or drifted away, but some of it collected in the orbital region nearby, and over time, gravity pulled those pieces together into Hippocamp. Hippocamp is a moon born from the wound of another moon. This kind of secondary moon formation, a moon built from the impact debris of a moon that survived, had been theorized but never definitively observed before Hippocamp. Its discovery opened up a new category of moon formation that scientists are now looking for in imagery of other planetary systems. 9 years of data, dozens of previous examinations, one moon hiding in the ring glow, and the only spacecraft that ever visited this system spent just 4 days here before moving on. The year was 1977. NASA launched 2 spacecraft, Voyager 1 and Voyager 2, on a mission to take advantage of a rare planetary alignment that would not repeat for 176 years. The 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, were arranged in a configuration that allowed a spacecraft using gravitational slingshot maneuvers to visit all 4 in sequence, without needing anywhere near enough fuel to reach them independently. Voyager 2 took this grand tour trajectory after visiting Jupiter in 1979, Saturn in 1981, and Uranus in 1986. Voyager 2 reached Neptune in August of 1989. It had been traveling for 12 years. The team at the Jet Propulsion Laboratory that had planned and executed the mission was a mix of veterans and younger scientists who had spent their entire careers leading up to this moment. The flyby window at Neptune lasted approximately 4 days. 4 days to gather as much data as possible about a planet, its moons, its rings, its magnetic field, and its atmosphere. The spacecraft was moving fast enough that the encounter was over before most of the raw data had even been fully transmitted back to Earth. Scientists on the ground were looking at images of Neptune's clouds while simultaneously trying to analyze data from instruments, measuring the magnetic field from a distance they would never get again. The harvest from those 4 days was extraordinary. Voyager 2 discovered 6 previously unknown moons. It confirmed the presence of the rings and captured images detailed enough to identify the arc structures in the Adam's ring. It measured the magnetic field and recorded its startling tilt and offset. It photographed the Great Dark Spot and the bright companion clouds. It captured close-up images of Triton's surface, including the active geysers. It measured wind speeds in the atmosphere and confirmed the retrograde equatorial flow. All of that from 4 days. But there is a sobering way to think about Voyager 2's legacy. Every major discovery made about Neptune since 1989 has come from telescopes hundreds of millions of miles away, doing their best to resolve details on a planet too far for any human-built craft to visit on short notice. The cloud disappearance, the mid-latitude auroras, the revised interior model, the discovery of Hippocamp, none of it benefited from proximity. All of it was pieced together from the kind of distant observation that leaves enormous gaps, Scientists built their standard model of Neptune largely from 4 days of close data collected 35 years ago and decades of fuzzy telescope images gathered since. And Voyager 2 is now more than 12 billion miles from Earth, having left the solar system entirely, still transmitting faint signals but long past Neptune. The case for a dedicated Neptune mission has been building for years, and what scientists want to know goes far beyond anything Voyager 2 could have captured. 4 days is enough to take a snapshot. It is nowhere near enough to watch a system breathe. Voyager 2 captured Neptune and its moons at a single moment in time. A single season, a single phase of the solar cycle, a single configuration of whatever storms were active that week. The data it returned was groundbreaking, but it was frozen, a photograph rather than a film. Everything scientists have learned since then points to Neptune being a place that changes. The dark spots form and dissolve on timescales of months. The cloud bands appear and vanish on timescales of years, linked to the 11-year solar cycle. The auroras, now confirmed to glow at the mid-latitudes in the infrared, could be shifting with the rotation of the lopsided magnetic field every 16 hours. Triton's geysers may be intermittent or seasonal. The ring arcs may be slowly dispersing despite the gravitational shepherding of Galatea. A spacecraft sitting in orbit around Neptune for even 2 or 3 years would capture more variability in that system than every observation ever made from Earth combined. The scientific community has recognized this. A report published by the National Academies of Sciences in 2022, a document that sets priorities for planetary science across the coming decade, ranked a Uranus orbiter with an atmospheric probe as the highest priority large mission for the next decade. Neptune received strong recommendations for a flagship-level mission in the following decade. The proposed Neptune mission concept, studied under names like the Neptune Odyssey concept, involves an orbiter and an atmospheric probe. The orbiter would spend years mapping Neptune's magnetic field, tracking storm cycles, monitoring the cloud system across multiple solar cycle phases, and studying Triton in detail that Voyager 2 could only suggest. The atmospheric probe would descend into Neptune's atmosphere, transmitting data for as long as it survives, measuring the chemical composition, temperature, pressure, and wind profiles at depths no telescope can see. The probe's descent into the atmosphere would answer questions that have been accumulating for decades. What exactly is the ratio of rock to ice to fluid in the interior? Where precisely does the superionic layer begin? How thick is it? Does the diamond rain actually occur at detectable rates? And at what depth does it start? What is the temperature profile through the cloud layers? And how does it change between the regions where dark spots form and the clear regions surrounding them? These are questions with answers sitting inside Neptune right now, waiting for an instrument that has not been sent yet. The atmospheric probe would be destroyed by the increasing pressure as it descended, but before that happened, it would send back data that could not be gathered any other way. A descendant of Voyager 2's legacy, designed to fall into the planet Voyager 2 only glimpsed. And while scientists plan that future mission, the region beyond Neptune has already handed them a discovery so unexpected that it forced a rewrite of what the outer solar system even is. Past Neptune's orbit, the solar system does not end. It just gets emptier and stranger. The region beyond Neptune is called the Kuiper Belt, a vast disk of icy objects ranging in size from small rocks to dwarf planets like Pluto. These objects are the leftover building blocks from the solar system's formation, preserved in the cold far from the sun's heat, some of them essentially unchanged for 4.5 billion years. Most Kuiper Belt objects are too small and too cold to hold on to any atmosphere. Holding a gas atmosphere requires gravity strong enough to prevent gas molecules from escaping into space. The warmer a gas gets, the faster its molecules move and the easier it is for them to escape. This is why Earth's moon has no atmosphere. Its gravity is too weak to hold one. Smaller objects have even less gravity, and at the temperatures of the Kuiper Belt, where even the coldest gases freeze solid, atmospheres should not form at all. Then, in 2023, a team of astronomers detected something they had not expected: a Kuiper Belt object formerly designated 2002 XV93, a body measuring roughly 310 miles across, smaller than the state of Texas, appeared to have an atmosphere clinging to it. The discovery came through a technique called stellar occultation. When a small solar system body passes in front of a distant star, the starlight dims slightly before the object fully blocks it. If the object has an atmosphere, the starlight dims gradually as it passes through the atmospheric layers, rather than cutting off sharply. The gradual dimming is the signal. The signals from this small object showed exactly that pattern: a thin, tenuous atmosphere extending above a body far too small to logically hold one. The question was immediate: where was the atmosphere coming from? A body this size at this distance from the Sun should lose any atmosphere to space over timescales much shorter than the age of the solar system. Gravity alone cannot explain the atmosphere's persistence. Something must be replenishing it continuously. Scientists proposed two main candidates. The first is cryovolcanism, the icy equivalent of volcanic activity. If the interior of this small body contains pockets of volatile material, compounds that vaporize at very low temperatures, and if something is generating enough internal heat to trigger eruptions, those eruptions could continuously pump fresh gas into the space above the surface, replacing gas lost to space before it fully disperses. The second candidate is comet-like activity triggered by a recent impact. A collision with another Kuiper Belt object could have excavated fresh, volatile material, exposing it to the near vacuum of space and allowing it to sublimate into a temporary atmosphere. Both explanations require the outer solar system to be more dynamic, more geologically alive than scientists assumed. The frozen, dead edge of the solar system turns out to be neither. The discovery of an unexpected atmosphere around a Kuiper Belt object landed in the scientific community the way a stone lands in still water. The ripples spread immediately. Before this discovery, the standard picture of the Kuiper Belt was a graveyard. Objects formed in the early solar system, frozen solid over billions of years, slowly drifting in near unchanging orbits, occasionally nudged into the inner solar system by gravitational interactions to become comets, but otherwise stable and inert. The Kuiper Belt was the part of the solar system where time had stopped. That picture required revision. If a 310-mile wide object could maintain an atmosphere through active internal processes or recent geological events, then the Kuiper Belt is a place where things are still happening. Collisions between Kuiper Belt objects occur regularly on astronomical timescales. Tidal heating from gravitational interactions with Neptune can affect objects in specific orbital resonances. Radioactive decay in the rocky components of these icy bodies generates heat over billions of years, potentially enough to trigger subsurface activity in larger objects. Pluto, the most studied Kuiper Belt object, has already forced a revision of this graveyard picture. When the New Horizons spacecraft flew past Pluto in 2015, it found a world with nitrogen glaciers that flow, a haze-filled atmosphere, and a possible subsurface ocean. Pluto is geologically active. The detection of an atmosphere around a much smaller, less studied object pushes this recognition further. Pluto might be the most dramatic example of outer solar system activity, but it may not be the exception. It may be one example among many. This matters for the search for conditions that could support life, a topic that generates enormous scientific interest and considerable caution in how scientists frame their conclusions. Liquid water is the requirement scientists focus on most consistently, and liquid water requires heat. The realization that multiple bodies in the outer solar system may have internal heat sources capable of melting ice at depth, whether from tidal forces, radioactive decay, or ongoing geological activity, means that subsurface liquid water could potentially exist in more places than anyone seriously considered 2 decades ago. Scientists are careful to note that the presence of liquid water does not imply life. The gap between water existing and life arising is enormous and poorly understood, but the existence of water is a necessary starting point and the outer solar system keeps producing evidence that water in liquid form may be far more widespread in our solar system than once believed. The edge of the solar system, the region that was supposed to be the dead zone, is full of heat, chemistry, and activity that we have only barely begun to map. And at the center of all these outer solar system mysteries, generating the most debate among scientists studying giant planet interiors, is a question about Neptune's core that has been open for decades. The excess heat coming from Neptune is one of the most argued over topics in planetary science. The planet radiates roughly 2.6 times more energy than it receives from the Sunday. That number has been confirmed repeatedly across decades of measurement. The disagreement is about the source, and the two main camps have fundamentally different ideas about what is happening inside Neptune. The first camp argues the heat is primordial. When Neptune formed 4.5 billion years ago, the violence of its assembly, billions of collisions between planetesimals, released an enormous amount of energy. That energy heated the planet's interior to extreme temperatures. Since then, the planet has been slowly cooling, bleeding that formation heat outward over billions of years. Under this model, Neptune is simply a very slowly cooling object, still warm from its own violent birth, and will continue radiating excess heat for billions of years to come as it works toward thermal equilibrium with its environment. This explanation is comfortable. It requires no unusual ongoing processes. It matches how scientists understand the thermal evolution of other large planets. Jupiter also radiates more heat than it receives, and the primordial heat explanation is widely accepted for Jupiter. The second camp argues that diamond rain is a significant ongoing contributor. The laboratory confirmation of diamond formation under Neptune-like pressures gave this camp real experimental support. If carbon atoms are continuously forming diamonds, and those diamonds are continuously sinking through thousands of miles of fluid mantle, the gravitational energy released by that sinking, converted to heat through fluid friction, represents a real and ongoing power source. The key question is scale. Laboratory experiments confirmed the process happens. They did not confirm how much diamond rain actually occurs inside Neptune or at what rate. Scaling from a microscopic experimental result to the interior of an entire planet requires assumptions that scientists disagree on. A third possibility, smaller in the debate but present, is that the radioactive decay of heavy elements distributed through Neptune's rocky interior contributes meaningfully to the heat budget. Certain isotopes of uranium, thorium, and potassium release energy as they decay over geological time. If Neptune's interior contains enough of these elements in the right proportions, their decay could add a continuous stream of heat alongside whatever primordial warmth remains. Most scientists believe the answer is some combination of these sources. The debate is about which one dominates and what that implies for how Neptune will evolve over the next several billion years. A planet running primarily on primordial heat is gradually cooling toward a quieter future. A planet running significantly on diamond rain is running a geological engine that changes as the methane supply shifts. A planet with significant radioactive heating is on a slow, steady curve determined by the half-lives of its isotopes. The correct answer changes the long-term forecast for Neptune's atmosphere, its storm cycles, and ultimately the fate of Triton and the ring system that will eventually replace it. And the answer is sitting inside Neptune right now, in a region humans have never reached and currently have no way to reach. Getting to Neptune is hard enough. Voyager 2 took 12 years to arrive, and it was using a gravitational slingshot trajectory that aligned planets to do most of the work. A dedicated orbiter mission using conventional propulsion would take a similar amount of time. A faster spacecraft using more advanced propulsion systems, concepts being studied but not yet built, could potentially cut that to under a decade. Getting inside Neptune is a different problem entirely. The atmospheric probe concept included in mission proposals would descend into Neptune's upper atmosphere, transmitting data as it fell, but the probe would not reach the interior. The crushing pressure of Neptune's deep atmosphere would destroy any currently conceivable instrument long before it reached the fluid mantle. Scientists estimate the probe might survive long enough to sample the atmosphere down to a pressure of roughly 10 times Earth's surface atmospheric pressure, possibly more with hardened design. For comparison, the pressure at the level where diamond rain begins is estimated to be millions of times Earth's surface pressure. The probe would not get close. Everything scientists hope to learn about Neptune's deep interior must come from indirect measurements. Gravitational field mapping from orbit, seismic-like wave studies. If scientists can detect oscillations in the planet's atmosphere that reflect internal structure, magnetic field measurements so precise that models can work backward from the field shape to the structure of the generating layer. This makes Neptune uniquely challenging among the planets we have identified as scientifically critical. Mars has been invaded by rovers. Venus had probes that survived its surface long enough to transmit images and chemical readings. Jupiter's Galileo probe descended into the gas giant's atmosphere in 1995 and transmitted data for nearly an hour before being crushed. The depth Galileo reached told scientists an enormous amount about Jupiter's chemistry. A Neptune probe would face all the same eventual destruction, but would need to survive a journey through an atmosphere far colder at the top and with chemistry that Galileo's designers never had to account for. The knowledge gap at the center of Neptune's science is permanent in the short term. Scientists will have to work around it through increasingly precise remote measurements, better computational models, and laboratory experiments that push the boundaries of recreating planetary interior conditions on a small scale. Every experiment that gets closer to recreating Neptune's interior conditions narrows the gap slightly. The diamond rain confirmation was one such step. Future high-pressure experiments targeting the behavior of water and ammonia under Neptune's deep mantle conditions will be others. The deepest layers of Neptune remain the most private interior in our solar system, a world within a world that has never been touched, never sampled, never directly observed, and will not be for a very long time. But what makes this matter beyond Neptune is what the planet's strangeness has done to the entire field of planetary science. Every wrong assumption scientists held about Neptune cost them somewhere else. When the standard Neptune model assumed a clean, layered interior with a small rocky core, scientists applied similar interior models to ice giants they found orbiting other stars. Astronomers have now confirmed thousands of planets around distant stars, and a large fraction of them fall into the ice giant category, planets with masses similar to Uranus and Neptune. If the interior model for Neptune was wrong, the interior models built from it for those thousands of distant planets were also wrong. The revised picture of Neptune's interior, more rock-heavy, more thoroughly mixed, more dynamically complex, now forces planetary scientists to go back and reinterpret the properties of every ice giant they have measured by other means. The mass, the density, the radius, the estimated composition of dozens of confirmed exoplanets all need to be reconsidered through the lens of what Neptune has taught scientists about how ice giants actually build themselves. This is why a single planet at the edge of our solar system carries consequences for our understanding of planetary systems across the entire galaxy. The vanishing clouds linked to the solar cycle carried a similar ripple effect. Scientists had largely assumed that planets far enough from their star would be isolated from stellar activity. Neptune's cloud behavior proved that ultraviolet radiation from the Sun can drive significant atmospheric chemistry across nearly 3 billion miles. This means that when astronomers study ice giants around other stars, they need to factor in the host star's activity level as a driver of atmospheric change, even when the planet sits far from its star. The mid-latitude auroras add another layer. The assumption had been that a planet's aurora location could be used as a simple map of its magnetic field structure, with auroras marking the magnetic poles. Neptune's auroras, forming in the wrong place, demonstrate that a highly tilted, offset magnetic field can produce aurora distributions that bear no simple relationship to the rotational axis. For exoplanets, where scientists try to infer magnetic field properties from detected auroral emissions, Neptune is now a warning that the relationship between aurora location and magnetic pole is not always straightforward. Each discovery about Neptune has provided a calibration point for planetary science as a whole. Calibration sounds technical. What it means in practice is that every time Neptune broke a rule scientists thought was universal, it saved them from applying that wrong rule to 100 other worlds. Neptune is the most distant known planet in our solar system, and it turns out it is one of the most instructive. A broken model is only a problem until the planet that breaks it teaches you the better one. And the biggest improvements to those models are still waiting to happen, dependent on a mission that scientists are pushing for, and funding bodies are evaluating, and engineers are already beginning to design. Somewhere in the long corridors of NASA and the European Space Agency, a mission is being designed. It does not have a confirmed launch date yet. The funding is still working its way through the complicated systems that decide where billions of dollars go in planetary exploration. But the scientific case for a dedicated Neptune mission is stronger now than at any previous point in history, and the discoveries of the past few years have only made it stronger. The proposal that has received the most detailed scientific study goes by the name Neptune Odyssey. It envisions an orbiter that would travel to Neptune and spend years in orbit, circling the planet, mapping it, watching it across multiple phases of its 16-hour rotation, its storm cycles, and eventually across a full 11-year solar cycle, if the mission is long enough. Alongside the orbiter, a probe would be released to fall into Neptune's atmosphere. The probe's descent would be brief by human standards, minutes or hours, depending on how deep it survives. But in that time, it would collect chemical readings directly from inside the cloud layers, measure temperature and pressure at depths no telescope has ever accessed, and sample the composition of the atmosphere with instruments that do not need to peer through billions of miles of space to get their data. Scientists want to know whether the ratio of hydrogen to heavier elements in Neptune's atmosphere matches what the interior models predict. They want to measure the exact abundance of noble gases, elements that do not react with anything and therefore act as pure traces of where the planet's material originally came from. The noble gas ratios in a planet's atmosphere tell scientists about the conditions in the early solar system where that planet formed. Preserved in the atmosphere like a chemical fossil, the orbiter would also dedicate significant observation time to Triton. Every flyby Voyager 2 made of Triton lasted only hours. An orbiting spacecraft could conduct dozens of close passes across years, mapping the full surface, measuring the geyser activity in detail, sounding the interior for evidence of the subsurface ocean that scientists believe may exist. If a subsurface ocean is confirmed on Triton, the scientific implications are significant. A world orbiting in the wrong direction, captured from the outer solar system, geologically active from tidal heating, sitting in a deeply tilted magnetic field, and harboring liquid water beneath its frozen surface, would become one of the most studied objects in planetary science. The question of whether life-supporting conditions could exist in places so far from any star would take a concrete step toward a real answer. The mission would also study the rings, the inner moons, Hippocamp and Galatea, and the arc structure of the Adam's ring, and the relationship between all of them and the magnetic environment that Neptune generates. The Neptune system is a complete scientific laboratory, a planet that has shattered assumptions about weather, magnetism, geology, and planetary formation. Moons that carry records of violent events from the solar system's first few 100 million years. Rings held together by gravitational mechanics that took decades to understand. 2.8 billion miles away from us, still turning, still glowing in the infrared, still raining diamonds in the dark, waiting